All right, folks, the next integration technique we're going to study is called partial fractions, or you may hear me call it partial fraction decomposition. To motivate why it is we need to, or we'd like to learn this technique called partial fraction decomposition, let's take a look at an integral that currently we can only attack using techniques from the prior section. So let's consider the integral 4 over 49x squared minus 4 dx. Okay, I can begin by pulling that 4 that's in the numerator out front and rewrite it as 4 integral 1 over, and then notice that, in the denominator, I've rewritten the 49x squared as the quantity 7x squared, and then the 4 as a 2 squared. By doing so, I can do a trig substitution. A is equal to 2, 7x equals 2 secant theta, which gives us x equals 2/7 secant theta. And as a result, dx would be 2/7 secant theta tangent theta d theta. So we're going to go through, an old trig substitution. So going through a trig substitution, that gives us that the integral 4 times the integral 1 over 7x quantity squared minus 2 squared dx. Thanks to trig sub, that is equal to 4 times the integral 1 over 4 secant squared theta minus 4 times 2/7 secant theta tangent theta d theta. So, with the 7x equals 2 secant theta, when you put 2 secant theta in here for the 7x, you get the 4 secant squared theta. Okay, that's looking like a mess. But we're going to continue. So continuing, so let me say that's where we left off on the previous slide. So it looks to me like what we can do here in the denominator is factor out a 4. And then what I can do is I can take a 1/4 and rip it out front because it's a constant, and the 2/7 and rip it out front to get this mess. 2/7 integral 1 over secant squared theta minus 1 times secant theta tangent theta d theta. All right, now remember, we know the Pythagorean identity. 1 plus tangent squared theta equals secant squared theta. So this secant squared theta minus 1, that's the same thing as tangent squared theta. So that's where I'm at. Looks like I'm making some progress. It looks like I'm making some progress because next, hopefully you say, well, let's cancel out those tangent thetas to give that. So now I'm definitely making some progress. Now, this integrand, secant theta over tangent theta. Well, I can look at that as, secant theta is 1 over cosine. Tangent theta is sine over cosine. So 1 over cosine over sine over cosine. That would simplify to 1 over sine, which is cosecant theta. So the secant theta tangent theta simplifies to cosecant theta d theta. Now there is a formula on what the antiderivative of cosecant theta happens to be. And I'm just going to use that formula now to get the antiderivative as being 2/7 natural log absolute value cosine theta minus cotangent theta plus c. So now we have to get rid of the thetas and we have to go back to the x's. And that's going to involve, looking at a right triangle. We know that's part of our trig substitution. So I'm going to head off to the chalkboard to do that and to finish this problem. All right, folks, picking up where we left off. This is where we left off. 2/7 natural log absolute value cosecant theta minus cotangent theta plus c. And I went ahead and put over there, the right triangle that matched up with the trig substitution. We let 7x equal 2 secant theta. That was our trig sub. if you divide by 2, you get what secant theta is. And we know the reciprocal of secant is cosine, so that gives us cosine theta is 2 over 7x. And sine theta from the right triangle is opposite over hypotenuse. So we have sine theta is square root 49x squared minus 4 all over 7x. All right, so got a lot of work ahead of us here. Cosecant theta. Well, since we know what sine theta is, we know cosecant's the reciprocal. So cosecant would be 7x over the square root of 49x squared minus 4 minus cotangent. Well, cotangent is cosine over sine. Or I could think cotangent's the reciprocal of tangent. My right triangle tells me quickly tangent, remember that's opposite over adjacent, tangent would be square root 49x squared minus 4 over 2. So the reciprocal of that is cotangent. So that's a 2 over square root 49x squared minus 4. Oh, we're going to clean this up a little bit. Notice in here, inside the absolute values, we have a common denominator, so we might as well make it one fraction. 7x minus 2 over the square root of 49x squared minus 4. And, well, I noticed something here under the radical. The 49x squared minus 4. That is easily factored. It's the difference of two squares. So I'm going to go ahead and factor what's under the radical as 7x minus 2 times a 7x plus 2. Hey, I should be able to go a step further in simplifying. Remember that square root can be rewritten as an exponent of 1/2. So I can rewrite using a property of exponents each of these factors with an exponent of 1/2. So let me do that. 7x minus 2 to the 1/2 and then 7x plus 2 to the 1/2. And give a little room here. Pulling this up here, when the bases are the same and you're dividing, you subtract the exponents. So I have a 7x minus 2, that's to the first power up here, and a 7x minus 2 to the 1/2 power in the denominator. Those bases are the same and we're dividing, so we subtract the exponents. So 1 minus 1/2 is 1/2. So I've at least simplified it down to this. It's not too bad. I'm going to go one more step in simplifying. Since I have this to the 1/2 power and that to the 1/2 power, it's the numerator to the 1/2 power, the denominator's to the 1/2 power, I can just make it the fraction 7x minus 2 over 7x plus 2, all of that raised to the 1/2 power. So that's an old property of exponents. Let's see. I could go one more step. There is a property of logarithms. You may have been told, like a law of logarithm, that you can, when you have a log and you see an exponent, you can move the exponent out front. So 1/2 times 2/7 is 1/7. And, boy, that was a lot of algebraic simplification. Good, clean fun with algebra. I'm going to write this one more way. One more way. an old property of logarithms, laws of logarithms. You have the natural log of a quotient. You could write that as subtraction. So I could write this as 1/7 the natural log absolute value 7x minus 2 minus 1/7 the natural log 7x plus 2 plus c. You know, either one of those. I could rewrite it like that. You're going to see why I wanted to write this down in a minute. So I wanted to go through all of this. This is a very long, ended up being a long problem with this trig substitution. There was a lot of algebra simplification. So we're going to head back to the slides. You'll see why I wanted you to see this. And we're gonna look at something that's pretty cool. So let's head back to the slides. All right, folks. All I can say is, wow, we just did a lot of work. We did a trig sub, and we did a lot of algebraic simplification. We just did a lot of work to do that integral. Now, what if I just solve this? 1 over 7x minus 2 minus 1 over 7x plus 2. And let's say I wanted to get a common denominator here to make one fraction. Well, let's go through the process of getting a common denominator. So the common denominator would be 7x minus 2 times 7x plus 2. So this fraction would be written like this with the common denominator, and this fraction is written like this with the common denominator. And well, now I'll write it as one fraction. You know, it's the whole point of getting a common denominator. So we have 7x plus 2 minus the quantity 7x minus 2 all over the 7x plus 2 times 7x minus 2. Now, if I clean up that numerator, you know, I could distribute that -1 and then combine like terms. You know, I end up with 4 over 7x plus 2 times 7x minus 2. And if I multiply out the denominator, look at what I get. So 1 over 7x minus 2 minus 1 over 7x plus 2 equals 4 over 49x squared minus 4. Since we know 1 over 7x minus 2 minus 1 over 7x plus 2 is equal to 4 over 49x squared minus 4, we could write that integral that took a lot of work for us to do. That integral of 4 over 49x squared minus 4 dx. We could rewrite it like that. And if we rewrite it like that, you know, it is so friendly to integrate 1 over 7x minus 2. And it's so friendly to integrate 1 over 7x plus 2. We can quickly and we can easily integrate that to get a 1/7 natural log absolute value 7x minus 2 minus 1/7 natural log 7x plus 2 plus c, or, you know, I could use a property of logarithms to get that as a result. So if we had noticed 4 over 49x squared minus 4 could be rewritten as 1 over 7x minus 2 minus 1 over 7x plus 2, man, look how easy that integration is. And that's the whole purpose of partial fraction decomposition. The whole purpose is to reverse that process so that we can write 4 over 49x squared minus 4 as 1 over 7x minus 2 minus 1 over 7x plus 2. In general, you know, when doing partial fraction decomposition, we're going to factor the denominator completely. So for the scenario that we've just been working with, the 4 over 49x squared minus 4, we would rewrite that as 4 over, you know, factor the denominator completely, which is 7x minus 2 times 7x plus 2. And so in partial fraction decomposition, our objective is to is going to be, for this situation, to find values for a and b such that 4 over 7x minus 2 equals a over 7x minus 2 minus b over 7x plus 2. So partial fractions, we want to determine the a's and b's. I mean, we know for this situation, a is 1 and b is 1, but that's the whole point of partial fractions. How do we get that a and how do we get that b? It's going to make our integration a lot easier if we can determine the a and the b. All right, now your book has several procedure boxes in this section for partial fraction decomposition. I mean, it has a procedure box on page 548, another one on page 550, one on page 552, and then finally on page 564, there's like a decent summary. These procedure boxes makes it seem like this is a complicated process. It really isn't. I'm going to provide a procedure box on the next slide. I actually believe it's going to take 2 slides. I'm going to try to attempt to condense the book's 3 boxes, page 548, 550, and 552, into one box. But honestly, what I'm going to give you next, it too is going to look like a complicated process. But it really isn't. The best way to really understand partial fraction decomposition is through example. And we will do an example after we look at the procedure box that I come up with. In doing examples, you can actually reference each part of the procedure box I'm going to give you and hopefully see, yeah, it really isn't too bad. So here's my procedure box, trying to condense what the book has done. So the first thing I say is divide if it's an improper fraction. So in other words, if p of x over q of x, where p and q are polynomials, if it's an improper looking fraction, in other words, if the degree of p, the numerator, is greater than or equal to the degree of q, start off by doing polynomial long division. Divide p of x by q of x. And when you do that, polynomial division, you'll get a polynomial plus, like I'm calling it a p sub 1 of x over q of x. But that p sub 1 of x is going to be a degree that's less than q of x. Then apply the following steps to the remainder, p sub 1 of x over q of x, which is a proper fraction. So most of the time, folks, not all, but most, we're going to start off with something that's already a proper fraction, and we don't have to worry about polynomial long division. So most of the time, we'll be starting off here in what I call step 2, factor the denominator. You have to factor the denominator completely. And when you factor the denominator completely, it's going to be a product of just linear factors and quadratic factors. The quadratic factor would be prime or irreducible, means you can't factor it any further over the real numbers. So notice that I'm saying you factor it into the form of ax plus b to the m, or cx squared plus dx plus e to the n. And this is what I was referencing. It looks like this is a kind of bad process, but it really isn't. Once we do an example, you'll see this isn't bad. But step 2, factor the denominator completely. Step 3, for each linear factor in the denominator, for each linear factor of the form ax plus b to the m, the partial fraction decomposition must include the terms, I have a sub 1 over ax plus b plus a sub 2 over ax plus b quantity squared plus a sub 3 over ax plus b quantity cubed plus yada, 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 plus a sub m over the quantity ax plus b to the m power. Again, this looks not so nice. It looks kind of complicated, but it's really not that bad. It's just saying each linear factor must be accounted for. You have to set up a partial fraction for each linear factor in the denominator. So once you factor that denominator, Number 3 is telling you what to do with the linear factors. Number 4 is telling you what to do with the quadratic factors. And I'm not going to read through all of that. The only thing I'm going to point out is that for the quadratic factors, the denominator's a quadratic, the numerator will be linear, which is why I have it as a b sub 1x plus c sub 1, etc., because that is linear. Step 5, well, we're going to do algebra. We're going to use some algebraic techniques to determine the constants in the numerators in order to come up with the partial fraction decomposition. So again, I know this looks bad. It looks like it's, kind of a complicated procedure. It really, really isn't. It seems so much better when we actually crank through this procedure in an example. So in this example, we're going to evaluate the integral 3x minus 1 over x squared minus x minus 6 dx. So get this written down, because I'm going to head off to the chalkboard to work through it, and you're going to see, yeah, this partial fraction stuff isn't that bad. All right, so the method of partial fraction decomposition. All the little procedure boxes and even the procedures that I gave you, it looks kind of complicated, but it really isn't. You'll see as we go through this example, and you could look back at the procedure box that I gave, where I tried to simplify down all the procedure boxes that the book has. So you could look back to see how it matches up with each one of the steps. It's not that bad. So first things first, this is proper. The degree of the numerator is less than the degree of the denominator, so I don't have to worry about starting off with any polynomial long division. So now what I do is I bring my integrand over here, this rational function, I bring it off to the side, and I want to make sure everything is completely factored. Well, the numerator's already factored. I want to factor the denominator, x squared minus x minus 6. So I believe that factors to x minus 3 times x plus 2. So the process of partial fraction decomposition is I have to have one term over here that I'm going to write down. I have to have one term for each factor that's in the denominator. So I have to have a term for the factor x minus 3, and I have to have a term for the factor x plus 2. Now the numerators are going to be constants. The numerators will be a degree that's one less than the degree of each of those denominators. So I generically put in an a and a b. Next, I take, this is an equation, and I multiply both sides of the equation by the least common denominator, which is x minus 3 times x plus 2. So when I multiply both sides by the least common denominator, I get a 3x minus 1 equals a times x plus 2 plus b times x minus 3. Okay, now here's where I will, kind of differ from the book. I wish the book would do this straight away. It doesn't, but I do. I need to pick values for x. I need to determine what the values are for a and b. So I'm going to pick values for x and toss into this equation and determine values for a and b. I can toss any number I want in for x, but I'm going to be strategic. I'm going to pick very convenient values of x to make my work a lot easier. What do I mean by an easy value of x? Well, I'm looking at this and I say, well, if x were negative 2, negative 2 plus 2 is 0, that would disappear. A times 0 is 0. And then I'll be able to immediately solve for b. So I put negative 2 in for x. So 3 times negative 2 is negative 6. Negative 6 minus 1 is negative 7. Negative 2 comes in for x. That's 0. Negative 2 comes in for x, and we get a negative 5b. Divide both sides by negative 5. I have determined b is 7/5. I still need to determine a. I can pick a different value for x, and I can pick any value for x that I want. But I'm going to look back to this equation and see, is there a convenient value of x to pick to maybe make my work a lot easier? And yeah, there is a convenient value of x. X equals 3. So if I put 3 in for x, I get an 8 equals 5a, and this is 0. So I immediately know that a is 8/5. So let me put this one step in right now, and I won't do this again. Here's where we're at. We said that our original integrand, we're trying to write it in this form. We know a is 8/5, so our original rational function can be rewritten as 8/5 over x minus 3 plus 7/5 over x plus 2. So I rewrite my original problem as 8/5 over x minus 3 plus 7/5 over x plus 2. And then the term-by-term integration should be very friendly. This is something we saw way back in section 8.1. You know, the general formula. It was a basic formula that I reviewed. And the antiderivative of the first term is just 8/5 natural log absolute value x minus 3 plus the antiderivative of the second term, 7/5 natural log absolute value of x plus 2. And that's all there is to it. The process isn't that bad. So here you go. I want you to practice the process. So you know the drill. Go to the exercises. Do number 29. Pause this video. Go do number 29. After you've done 29, restart the video. I'll be here at the board working through it. All right, in 29 you were asked to evaluate the definite integral from -1 to 2, 5x over x squared minus x minus 6 dx. So my integrand is proper. So I'm going to crank it through the process of partial fraction decomposition. And I notice the denominator factors. Actually, it factors just like the example that we did, which was kind of nice. And now I have to write down a fraction where I account for each factor in the denominator. So I have to write a over x minus 3 plus a b over x plus 2. Next, you multiply both sides of that equation by the least common denominator. That should have given you a 5x equals a times x plus 2 plus b times x minus 3. Pick some convenient values for x. For me, I would pick x is -2, and that would give me -10 equals 0, minus 5b. So that tells me b is 2. And then the next convenient value I would pick is x equals 3. So I get, let's see, 15 equals 5a plus 0. So a equals 3. So my original problem, thanks to partial fraction decomposition, I can rewrite this as 3 over x minus 3 plus 2 over x plus 2 very friendly to integrate each one of these. You get 3, the natural log absolute value of x minus 3 plus 2 times the natural log absolute value of x plus 2. And I need to evaluate this from -1 to 2. So let's see what I get. I get a 3. 2 comes in here. I get a -1. Absolute value of -1 is 1. So 3 natural log 1 plus 2 natural log of 4 minus, okay, -1 comes in for the x. That gives me a -4. Absolute value of -4 is 4. And see, -1 plus 2. -1 plus 2 is 1. Absolute value of 1 is 1. So I have 2 natural log 1. Now I should be able to clean this up a little bit because the natural log of 1 is 0. So this is 0. Natural log of 1 is 0, so the product is 0. So I have 2 natural log 4 minus 3 natural log 4. Well, 2 natural log 4 minus 3 natural log 4 is -1 natural log 4. That's all there is to number 29. So let's head back to the slides and see what is next. All right, folks, after that first example, and then I asked you to do number 29, hopefully you saw, yeah, Bill was right. The partial fraction decomposition isn't that bad. The words describing it are a lot worse than the actual doing it. So let's continue on. Looks like we're going to do another example here. We're going to evaluate the integral 5x plus 3 over x cubed minus 2x squared minus 3x. So get this written down because I'm going to head off to the chalkboard to do another one. All right, in this example, we're going to evaluate the integral 5x plus 3 over x cubed minus 2x squared minus 3x dx. All right, so it's proper, so I can just immediately get started on the process of partial fraction decomposition. So let me pull the integrand over here, and let me start factoring the denominator. I could take an x out. That leaves me with an x squared minus 2x minus 3. And then I got to factor. Hopefully this will factor. Let's see. X squared minus 2x minus 3. We have an x. We have an x minus 3 plus 1. So I have everything completely factored. So I need to set up, let me pull it down here. I need to set up a fraction for each denominator, each factor in the denominator. So that would give me the fraction a over x plus, got to take care of that factor now, b over x minus 3. Now this factor, c over x plus 1. So we have another fraction in there. It doesn't change the process. My next step is to multiply both sides of the equation by the least common denominator to get a 5x plus 3 equals a times x minus 3 times x plus 1 plus, okay, so when this gets multiplied here, I'm left with a b times x plus 1 plus c times x minus 3. Oh yeah, I want to pick convenient values for x here. So the values of x I would pick, well I guess the first one I would pick is x equals 0. So if I pick x equals 0, that gives me a 3 equals, so this is -3, this is 1. So that's a -3a. If x is 0, that'll be 0 and that'll be 0. So we immediately have a is -1. Moving on, the next convenient value for x that I would pick is -1. So let's see, negative 1 comes in here for x, that's negative 2. When negative 1 comes in here for x, well, this factor is 0, so that's gone. This factor is 0, so that's gone. So when negative 1 comes in here for x, see, that's a negative 1, that's a negative 4, negative 1 times negative 4, well, that's a positive 4, so we have a 4c. Divide both sides of the equation by 4, we get c is negative 1/2. We need to still determine b, and I have one more convenient number left to pick for x. That's x equals 3. So 5 times 3 plus 3 is 18. 3 comes in here for x. This factor is 0, so that's gone. This factor is 0, it's gone. So when 3 comes in here for x, we have 3 times 4. That gives us a 12b. Divide both sides by 12, and we get b is reduced down. B is 3/2. So, my original problem, this mess, I can rewrite it as a over x. That's negative 1 over x. Plus b, which is 3/2, over x minus 3, plus c, negative 1/2 over x plus 1. So instead of putting a negative 1/2 here, let me make this a minus 1/2 over x plus 1. So folks, we should be able to get the antiderivative now in one step. Negative natural log absolute value of x plus 3/2 natural log absolute value of x minus 3 minus 1/2 natural log absolute value of x plus 1 plus c. And for this one, that's where I will stop. I could simplify, I could use properties of logarithms, and I might on the next one. In fact, I'm going to have you do one right now. So pause the video, do number 35. Once you've done 35, restart the video, and I'll be here at the board working through it. All right, here we go. 35, you're asked to integrate x squared plus 12x minus 4 over x cubed minus 4x dx. So I bring my integrand over here, start factoring. I could take an x out of the denominator, so that leaves me with an x times x squared minus 4. Factor some more. X squared minus 4 factors to x plus 2 times x minus 2. Set up my partial fractions. A over x plus b over x plus 2 plus c over x minus 2. So, you know the drill. Multiply both sides by the least common denominator. That's the least common denominator. So when I do that, I get an x squared plus a 12x minus 4 equals a times x plus 2 times x minus 2 plus bx times x minus 2 plus cx times x plus 2. So yeah, we have some convenient values of x that we can select here. We can select x equals 0. We select x equals 0, that gives us a negative 4. See, those two terms would be 0. So negative 4 equals a negative 4a. So a is equal to 1. All right, the next convenient value I pick is x equals 2. See, when I pick x equals 2, so 2 comes in here for the x. You get 4 plus 24 minus 4. That gives you a 24. That's 0. That is 0. So 2 2 times 4 is 8, so you get 8c. So you end up with c is equal to 3. That's not bad. And then my final convenient value is x equals -2. So when you do x equals -2, let's see, you get a 4, -24 minus 4. That's a -24 you end up with. And let's see, -2. This would be gone, this would be gone. So you got a -2 times a -4. That's a +8. So b is -3. Okay. Now you might have a slightly different. I mean, if you put the x minus 2 here and the x plus 2 here, you'll just have a different value for b and c. It's not going to affect the final answer. So, here we go. We can now rewrite this as a over x, so that's just a friendly 1 over x, plus b over x plus 2, well, I'll make that, instead of plus a negative, I'll make it minus 3 over x plus 2. And then plus c is 3 over x minus 2. Very, very friendly to get an antiderivative here. Natural log absolute value of x minus 3 natural log absolute value of x plus 2 plus 3 natural log absolute value of x minus 2 plus c. If you look in the back of the book for this one, Bob, back of the book, probably doesn't have this as an answer. But you should be able to get your answer to match the back of the book. So here's what I think the back of the book would do here. It's going to use properties of exponents. So here's what I think Bob would do, back of the book. First is put the 3 back into an exponent position using properties of logarithms. So we have the natural log absolute value of x minus the natural log absolute value x plus 2 cubed plus natural log absolute value of x minus 2 cubed plus c. Next, I think Bob would use another property of logarithms that subtraction can be rewritten as division. So this would be the natural log of absolute value of x over x plus 2 quantity cubed. And then I think the back of the book would finally use a property of logarithms, a law of logarithms, that addition can be rewritten as multiplication. So you get the natural log of absolute value of this times this. So x times x minus 2 cubed over x plus 2 cubed plus c. Now I think this is what the back of the book would have. So I know a natural question that someone would have right now is, well, what would I like to see as a final answer? And I'll say that I'm fine here. But I wanted to go through this because you get this as an answer for 35 and you look in the back of the book and you see this. Again, don't assume that you're incorrect. Try to get your answer to match the back of the book, and it's just algebra. It's using laws of logarithms. So let's head back to the slides, see what is next. All right, that last example, and number 35, it's the same process. We just had one extra factor in the denominator, so we had to set up 3 separate partial fractions, but it's the process. It isn't that bad. And also in number 35, I kind of indicated, what a good answer would be. And I showed you, what I thought the back of the book or Bob would have as an answer. Just keep that in mind. You look in the back of the book, you might have to use some algebra to get your answer to simplify down to look like what's in the back of the book. So, hey, we're going to do another example. Remember I told you the best way to really see the process of partial fraction decomposition was through example. So here we're going to look at integrating 3x minus 4 over x squared minus 2x plus 1 dx. And in this example, we're going to see how we handle repeated linear factors. So get this example written down because I'm, heading off to the chalkboard to do it. All right, this example I wanted to just do real quick to show you how you handle what's called repeated linear factors. And I've already factored the denominator, so we're going to integrate 3x minus 4 over the quantity x minus 1, that quantity squared. So when you do, it's already factored, so when you do the partial fractions, you have to account for each of those linear factors. And I know this was written in the guidelines that I gave, but it's much easier to see, how you do this. So you have to account for the x minus 1 and the x minus 1 quantity squared. That's how you handle repeated linear factors. Now the process is still the same. Multiply both sides by the LCD to give you a 3x minus 4 equals a times x minus 1 plus b. Pick a convenient value. I think x equals 1 is a convenient value. So when you pick x equals 1, you get a negative 1 equals, negative 1 equals b. That was about as convenient as it gets. Now you need to pick another value of x. I've run out of convenient values to pick for x, so I can pick anything I want for x. I can pick any number I want for x. There are no more convenient values. I'm going to pick x equals 0. So when I pick x equals 0, that gives me negative 4 equals a negative a plus b. But folks, I already know what b is. b is negative 1. So I can just toss that in here for b. And add 1 to both sides. And now I know a has a value of 3. That wasn't too bad. So my original problem, I can rewrite that as a over x minus 1. So that's 3 over x minus 1 plus b over x minus 1 quantity squared. Well, b is negative 1, so I'll make this minus 1 over x minus 1 quantity squared. All right, this isn't too bad. We know the antiderivative here is 3 natural log absolute value of x minus 1. This one, getting the antiderivative here, it may take a little bit more work. Not that much more. I mean, it is not natural log absolute value of x minus 1 quantity squared. That little rule that we've already reviewed is only true when the denominator is linear. This is not linear. It's not that bad. Let me kind of just pull it over here. I'm trying to get an antiderivative for that. I'll use yellow chalk for it. Maybe the first thing I would do when I see this is say, well, this is the integral of x minus 1 to the negative second. And then if I were to do a u substitution on this, u would be x minus 1. du is dx. So I would just be integrating a u to the negative second. The power rule tells me that that would be negative u to the negative first. Well, negative u to the negative first, that would give me, that's not too bad. Negative u to the negative first, that's negative x minus 1 to the negative first, or negative 1 over x minus 1. So minus negative 1 over x minus 1. Not too bad at all. And I didn't write all those steps down here with the U sub. If you need to, you definitely do that. I want to see a correct answer. I verbalized each of the steps for the U sub over there, but not too bad. So here, I'd like you to practice this. I'd like you to practice one maybe with a repeated linear factor. So pause the video, do number 49, and once you've done it, restart the video. I'll be here at the board working through it. All right, number 49, you were asked to integrate x squared minus 4 over x cubed minus 2x squared plus x. So let's get to it. So I bring this over here, my integrand over here. I'm going to start factoring the denominator. I can take out an x. That leaves me with an x squared minus 2x plus 1. And if I continue factoring, I get x squared minus 4 over x. This factors to x minus 1 times x minus 1. It factors to x minus 1 quantity squared. Now I've refrained from factoring the numerator, and I'm not even going to bother factoring the numerator, because the numerator would factor to an x plus 2 times x minus 2. It would cancel with, there's no factor in the numerator that would cancel with a factor in the denominator, so I'm going to leave the numerator alone. In any event, to write the partial fractions for this, it would be a over x plus b over x minus 1 plus c over x minus 1 quantity squared. Go through the same process. Multiply both sides of this equation by the LCD, and that gives me an x squared minus 4 equals a times x minus 1 squared plus bx times x minus 1 plus cx. Hopefully you said the first very friendly, very convenient number to use for x is x equals 0. That gives you a negative 4 equals a. That's 0, so you immediately have negative 4 is equal to a. Hey, the next easy, convenient number I would use is x equals 1. So that gives us a negative 3 equals, that's 0. So we immediately know c is negative 3. So now we need to determine what b is. I've run out of convenient numbers to toss in for x, so I can put in anything I want for x. I'm going to pick x equals 2. I mean, that's pseudo-convenient, only because when 2 comes in here for x, we get a 0. So that's a 1 squared times a. See, this is 1, this is 2, so we get a 2b. And, we have a 2c. We know a is negative 4, so let's put negative 4 in for a. We know c is negative 3, so put negative 3 in for c. 2 times negative 3 is negative 6. So that's what, negative 10. Add 10 to both sides. You get 10 is 2b. b equals 5. So the original integral, we can write it as a over x. A over x, that's a negative 4 over x. Plus b over x minus 1. That's 5 over x minus 1. Plus c over x minus 1 quantity squared. Well, c is negative 3, so that's minus 3 over x minus 1 quantity squared. And very easy to do this integration. The antiderivative of negative 4 over x, that's negative 4. Natural log, absolute value of x. Antiderivative of 5 over x minus 1, that's 5. Natural log, absolute value of x minus 1. It's this integral that we'd have to do just a little bit of work on, so maybe, as an aside, I would say, you write that as 3 times x minus 1 to the negative second, or 3 integral x minus 1 to the negative second. And then I'm not going to finish it off. You could let u equal x minus 1, get an antiderivative, resubstitute, and you would get the antiderivative for this as 3 over x plus 1. Let me put a box around it and say that looks good. I know Bob doesn't have that. I know what Bob would do is put them back into exponent positions, use properties of logarithms, and I'm just going to leave it like this. So, and hopefully you can get your answer, this answer, to match what Bob has. So that's it for 49. Let's head back to the slides. I think we're going to do one more example where in the denominator we have an irreducible or prime quadratic factor. And we'll see how to handle that. Let's head back to the slides. All right, so doing repeated linear factors didn't seem too bad. This is going to bring us to our final example here in this section, which is evaluating the integral 2x cubed minus 4x minus 8 all over x times x minus 1 times x squared plus 4 dx. So this is the one example I'll look at on what we need to do when we have a quadratic factor, x squared plus 4. That's a quadratic factor. Give you a heads up right now, this example is really involved. It's like one of the nastiest examples I could find to do right now. There's just a lot going on in it. I don't think you'll see anything in the homework nearly as bad as this example. But let's head off to the chalkboard and work through it. All right, in this example, we're going to evaluate the integral of 2x cubed minus 4x minus 8 all over x times x minus 1 times x squared plus 4 dx. This example is going to be really involved. It's probably the nastiest example I could find because of everything that's involved with it. But I did make it kind of friendly for us to start off. I have the denominator completely factored. That's a linear, that's a linear, that's a quadratic. It's said to be irreducible or prime. You can't factor it any further over the real numbers. So we begin the process. 2x cubed minus 4x minus 8 over x times x minus 1 times x squared plus 4 equals, now we do the partial fractions, so we have an a over x plus a b over x minus 1 plus, now we have to take care of the factor x squared plus 4. Because it's quadratic, its numerator has to be a degree that is 1 less. That means the numerator has to be a linear. So it's not just a number c I'm putting up there, it's linear. It's a cx plus d. Multiply both sides by the LCD to get a 2x cubed minus 4x minus 8 equals a times x minus 1 times x squared plus 4 plus a bx times x squared plus 4 plus a cx plus d times x minus 1. Okay, find some convenient values. I think x equals 0 is a convenient value. So when we pick x equals 0, that will be a negative 8. See, that's a negative 1, that's 4, so we get a negative 4a. That's 0 and that's 0. Alright, so we have a is 2. So far so good, that's not too bad. Looking for another convenient value, and I think it's x equals 1. That's the next convenient value. So 1 comes in here for x, 2 minus 4 minus 8, that's, I'm sorry, you got 2 minus 4 minus 8, we get negative 10. Let's see, this will be 0 thanks to that factor. This will all be 0 thanks to that factor. So what do we have here? A 1. 1 plus 4 is 5. So we get a 5b. So we get b is negative 2. All right, so far so good. But now we need to get c and d. There are no more convenient values to pick for x. I mean, we've exhausted all of our convenient values. So here's what I'm going to do right now in order to get c and d. I'm going to look at this, and I'm going to substitute in what we've determined a and b to be. I'm going to put 2 in for the a, negative 2 in for the b. So I'm going to rewrite this equation. 2x cubed minus 4x minus 8 equals 2 times x minus 1 times x squared plus 4 minus 2x times x squared plus 4 plus cx plus d times x minus 1. Just barely had enough room to get that on there. Alright. I have to pick a value for x. I can pick anything I want for x. I can pick any value for x and substitute it in. I want to pick kind of small numbers actually, so I'm going to pick x equals negative 1. So when I put negative 1 in here for x, this will be a negative 6. Over here, oh boy, let's see, that's a negative 2, 5, that gives me a negative 10, and negative 1 comes in for all those x's. Oh boy, so let's see, what do I get? I better write this down. Negative c plus d, there's a negative 1. And negative 1 minus 1 is negative 2. So negative 1 times negative 2 is 2. So if I distribute that 2 on through, I would get negative 2c plus 2d. Or if I add 10 to both sides, I get 4 equals negative 2c plus 2d. I now need to pick another value for x. And this time I'm going to pick x equals 2. Keep in mind, I'm tossing it into this equation. And when I toss negative 2 into this equation for x, I'll end up with 0 equals, let's see, 16 minus 32 plus a 4c plus a 4d. I'll let you do the arithmetic to make sure I did that correctly. But in other words, I'm going to get a 16, that's negative 16, add 16 over here, equals 4c plus a 4d. In order to determine c and d, this is an old algebra problem, I need to find the simultaneous solution to this system of equations. So, I'm running out of room, so I'm going to have to do a little erasing. I need to make note of what I've already determined. I've already determined a is 2. So let me kind of write that up here. I've determined a is 2, and I've determined b is negative 2. But I'm going to erase this. before I do too much erasing, let me write down my system of equations here. 4 equals negative 2c plus 2d, and 16 equals 4c plus 4d. All right, so you learned a lot of techniques on solving systems of equations. You learned the substitution method. I'm going to cut to the chase and do the elimination of a variable method. All right, there are many ways to solve. I have a typo here. Let me take care of my typo on the board. This should be 16 equals 4c plus 2d. I could solve this system of equations by the method of substitution. I could solve this system of equations by using matrices. I could solve this system of equations by doing the elimination method, which is the method I'm going to use, the elimination method. It's probably the method that you hopefully will remember once I do it. The elimination method says I would multiply both sides of the first equation by 2, and after I do that, I add the two equations together to get 24 equals 6d. Divide by 6, we get d is equal to 4. Now we just need to find c. And I could take this value of d and substitute it into either one of these equations here. It doesn't matter which. And I would get c is equal to 2. So a lot of algebra we've done just so we can rewrite the original integral as a over x, so that's a 2 over x, plus b over x minus 1, so that's minus 2 over x minus 1, plus cx plus d, that's 2x plus 4 over x squared plus 4 dx. And that's easy to integrate, that's easy to integrate. This one requires a little bit of work. So here's what I will do. Just kind of looking ahead a little bit, I'm going to rewrite this mess as 2x over x squared plus 4 over x squared plus 4. So basically I'm using the concept of a common denominator. And hopefully you see why I want to do that. I can evaluate this integral with a very basic u substitution. This one here is it's inverse tangent. So I get, as an antiderivative, like I said, this is easy, 2, the natural log absolute value of x. This was easy, 2, natural log absolute value of x minus 1. This one isn't too bad because when you do the u sub, you're going to end up with a 1 over u. So that's the natural log absolute value of x squared plus 4. And like I said, this one, basic inverse tangent. So it'd be 4 times 1/2. So that's 2 inverse tangent x over 2 plus c. Very involved example. There was a lot going on. I want you to practice one of these. And I promise you, the one I want you to do is number 53. I promise you it's not as bad as this example we just did. I thought I would find one of the worst examples possible. 53 is not that bad. Pause the video, do number 53. When you're done, restart the video. I'll be here at the board doing it. All right, 53, you're asked to integrate 2x squared plus 5x plus 5 all over x plus 1 times the quantity x squared plus 2x plus 2. Denominator is already completely factored. We have a linear times a quadratic. I promised you this wouldn't be as bad as the last example we did. Let's see if that's actually the case. So, Come over here to start the process of partial fractions. A over x plus 1, and then my quadratic, I need to put in a bx plus c. Well, already it looks better than the last example because it's just smaller. Multiply both sides by the LCD. And this is what we get. All right, so convenient values of x. The first one I notice would be x equals -1. So let's see, when you put -1 in here for x, what do you get, a 2? And here, let's see what we get, 1 plus -2 plus, wow, that wasn't bad. This factor would be 0. That wasn't bad. We immediately have a is 2. All right, so technically I've run out of convenient factors, so I'm now going to pick x equals 0. And let's see, that gives me a 5 equals a 2a plus, well, that's not bad. That's 1. This is 0, so I'm left with the c. It's not bad because we know a is 2. So we get c is 1. All right, so far so good. Next, see, I picked -1, 0. I'd probably pick x equals 1. And when I pick x equals 1, let's see, here I get a 12. Here I get a 5a. Here I get b plus c times 2. Well, let's use the numbers we know. We know a is 2. So 5 times 2 is 10. We've determined c is 1. So we have a b plus 1 times 2. So we get 12 equals 10 plus a 2b plus 2. 12 equals 12 plus 2b. B is 0. Now that's not bad. Much easier than the example I did. So let's finish this off. This I'll rewrite as a over x plus 1. I don't know why I have an x here. That's an x plus 1. I'm sure you all saw that, and it took me a long time to realize it. A over x plus 1 plus bx plus c. Well, b is 0, c is 1, over x squared plus 2x plus 2 dx. This integral is easy. This is the easy way. This one here requires a little bit more work. But it's not that bad. It's an old technique. I'm going to rewrite this as x squared plus 2x plus 1 plus 1. 1 plus 1 is 2. I can put those together in a group. It's a perfect square. It's x plus 1, quantity squared plus 1. So an old technique that we learned earlier in this section. And so we just finished it off real quickly. 2 natural log absolute value of x plus 1 plus inverse tangent of x plus 1 plus c. And hopefully you got that. That was number 53. That's it for this section. So now you can go do the homework. Thanks for watching.